Question 1. Fred's laptop. Fred has a laptop which can be powered either by the main supply, voltage transformed and rectified, so that means transformed down from 240 down to the 11.2 volts, and rectified means turns into DC as opposed to the AC that comes out of the wall, or can be run by a battery power source. When Fred takes the main supply plug out of her laptop, i.e. when these are disconnected, the battery begins to operate. The battery's over here with an internal resistance. Fred's laptop has a capacitor with a capacitance of 7.35 millifarads over here connected to the circuit to protect the laptop against a power surge that might occur when the battery starts to operate. The diagram below shows the circuit. While the main supply is connected, the voltage across the laptop is 11.2 volts. When the main supply is disconnected, a switching circuit, this one over here, delays the operation of the battery for a fixed period of time. During this time, the capacitor alone powers the laptop, i.e. we have the following blue circuit, and that is all that's in the circuit, a capacitor and a resistor. Question 1a. Show that the time constant for the capacitor circuit is 2.85 seconds. Using torr equals RC, time constant equals resistance times capacitance, where the resistance of the laptop is 582 ohms and the capacitance is 7.35 milli, or times 10 to the minus 3 farads. We can simply type that into our calculator. 582 times 7.35 e minus 3 gives us the answer that we're looking for, of 4.28 seconds. B. On the axis below, plot two accurate points and draw a voltage time graph for the discharge of the capacitor in the circuit. Well, initially it had 11.2 volts. Now it may help to put a scale on here going up in 2 volt increments and a time scale going along here at almost the time constant. Okay, it says plot 2 points. So here's our first point, and then what's happening is discharging, so it's going to decrease by 63%, or it's going to have 37% remaining. So we can simply come over to our calculator and go 11.2 times 0.37, because that's how much is going to be remaining, and we've got 4.14 volts after 4.2 seconds. Okay, so 4.2 seconds, we're going to have 4.1 volts. Okay, and then we go, well, what's after the next time constant? You don't actually need to do this because the question doesn't ask you. We end up having a decay curve looking something like that. Question C, estimate a sensible maximum for the time the switching circuit must delay the switching over, and show how this value was determined. Well, if we look back in the previous question, we can see that the battery needs 4.71 volts across it. So when the capacitor is supplying 7.41 volts, then the switching circuit should come on. So around 7.41 volts is when the switching circuit needs to come on, and we're looking down here at around 2 seconds. Or a written answer, something like battery voltage is 7.41 volts, so voltage should not drop below this. Also allow a safety margin. From the graph, we're looking at around 2 seconds. D. Fred needs to replace the capacitor. She only has 11 millifarad capacitors available. Draw a diagram to show how a number of these 11 millifarad capacitors can be connected together to achieve the required capacitance of 7.35 times 10 to the minus 3 farads, and justify your decision by calculating the total capacitance. There are a number of ways you could answer this question. Simplest is by having a capacitor in series with two capacitors in parallel. When they're in parallel, we simply add the capacitances. So this is just 11.0 times 10 to the minus 3 plus 11.0 times 10 to the minus 3, as an answer of 22 times 10 to the minus 3. 1 over the capacitance total is 1 over C1 plus 1 over the equivalent C2, or we could write capacitance total equals 1 over the 11, 1 over the 22, put that to the power of minus 1. We plug that into our calculator, brackets 1 divided by 11e minus 3 plus 1 over 22 e minus 3. Answer to the power of minus 1. We get our answer of 7.3 times 10 to the minus 3 farads is required. After Fred has been using her laptop for a while, the battery becomes flat and she plugs in the main supply. The main supply voltage has been transformed and rectified, so that means changes from 240 into DC at 18.5 volts. It powers the laptop and at the same time recharges the battery. The EMF, the electromotive force of the battery, is 7.41 volts. The circuit is shown below. When the switch is closed, a current of 3 amps flows through the main supply and 2.98 amps flows through the battery. So that's saying 3 amps comes out of the power supply and 2.98 amps goes through the battery in the wrong and inverted commas direction. Use Kirchoff's charge current law to calculate the current through the laptop resistance. Hopefully the answer to that question is pretty obvious. Essentially we're asking, what is the current going through the laptop? If there's 3 amps coming into that node, 2.98 going out, then the current here is going to be 0.02 amps. More formally, current through the laptop is equal to the current from the supply take away the current through the battery, which is 3 amps take away 2.98 amps, giving us an answer of 0.02 amps. F. Use Kirchoff's energy voltage law to calculate the internal resistance of the battery. Well, there are two ways of really answering this question. The first one is to use Kirchoff's voltage law directly. So if we just redraw the circuit, as of all Kirchoff's voltage law questions, the first thing you need to do is decide on which way you want to walk around the loop. I'm going to start up here in the top corner and walk around in a anti-clockwise direction. Okay, so we're going to go 582 times 0.02, and that's minus, because it would be minus IR because we're going in the same direction as the current. We come up here and our current's actually still going down, so we're going to add 2.98 R because we don't know what that resistance is, and we go from little to big, so we're going to add 7.14 volts, and the sum closed loop must be 0. In our calculator, minus 582 times 0.02 plus 7.41 gives us an answer of minus 4.23. So we've got 0.98 R minus 4.23 equals 0. So we can say that R is going to be 4.23 because we move it over to the right hand side, divided by 2.98. R is 1.42 ohms. Second method we could have used is by simply using Ohm's law. So what's the voltage across this resistor? Well, the voltage across this resistor must be the same as the voltage across this resistor and power supply, okay, because they're in parallel with each other. And so we could use V equals IR. The current is 0.2. The resistance is 582. So the voltage there is 11.64 volts. You may ask, well, why isn't it the full 18.5? When we look at the circuit over here, there's this 2.29 ohm resistor here, which is reducing the 18.5 volt supply. Okay, so there's 11.64 volts there, so that means there must be 11.64 volts there as well. And so we know that there's 7.41 volts there, so we can ask, well, what's the voltage across this resistor? Might just be easier if we redraw the circuit. We know that the current going through here is 2.98 amperes, and so if there's 11.64 across both of them, then the voltage across here must be 11.64. Take away the supply voltage of 7.41, making there be a voltage there of 4.23 volts. We use Ohm's law. R equals voltage divided by current. Voltage across that resistor is 4.23 volts. The current flowing through that resistor is 2.98 amps, giving us a resistance of 1.42 ohms. Two ways of doing the same problem. Question 2. Bob's bedroom is lit by a fluorescent lamp. A fluorescent lamp has a tube filled with gas at low pressure which glows when a potential difference of voltage is placed across it. Gas molecules are excited and momentarily ionized. The movement of these ionized molecules creates an electric current through the tube. Bob and Fred decide to investigate the circuit for Bob's fluorescent lamp. They find that the lamp operates with a DC supply of 250 volts, but the lamp requires a starter circuit to start the current flowing in the tube. In the diagram below, the starter circuit is in the middle branch. When the circuit is closed, a current of 8.03 amps flows through the inductor. No current flows through the fluorescent tube. The time constant for the circuit is 0.030 seconds. Calculate the resistance R of the resistor and round your answer to the correct number of significant figures. The formula we're looking for in terms of time constant is Torr equals L over R, where L is the inductance of the inductor, 0.932 henries, and R is the resistance which we're looking for, and we're being told that Torr is 0.030 seconds. So the resistance, we put that up and that down, so that's going to be 0.932 divided by 0.03, which gives us an answer of 31.0666 ohms. L here has been given to 3 significant figures, and time has been given to 2 significant figures. So our answer technically should be 31 ohms, 2 significant figures, because we always go to the least number of significant figures in the question. 2b, on the axis below, sketch a voltage time curve for the inductor when the switch is closed. On the voltage axis, mark the maximum voltage and the value when the time is at 1 time constant. So the maximum voltage is going to be the supply voltage, so that's 250 volts, and it's going to decay by 63% in 1 time constant. So another way of saying that is there's going to be 37% left, so I could times that by 0.37. So there's going to be 92.5 volts after time constant. Switch is then opened and the current in the circuit dies to 0 in 0.0100 seconds. A voltage is induced in the inductor. It is this voltage that starts the current flowing through the fluorescent tube. Calculate the starter voltage induced in the inductor. The formula we're looking for is epsilon equals inductance, change in current over change in time. The inductance from the other page is 0.932 henries. Change in current was from 8.03 amps to nothing, from 8.03 to nothing, and the time that took was 0.01 of a second. We type that into our calculator, negative 0.932 times 8.03 divided by 0.01, giving a voltage of negative 748.4 volts, or negative 748 volts to 3 significant figures. 3 significant figures, 3 significant figures, 3 significant figures. Done. Question 2D. Explain why opening the switch in the starter circuit will induce a much greater voltage across the inductor than there was when the switch was closed. Okay. Well, we know from Kirchoff's voltage law that the sum of the voltages around any closed loop must be 0. Okay, so there's 250 volts here. Okay, so that means between the resistor and the inductor, across those, the voltages across those two must be 250 volts, and the voltage across the fluorescent lamp must be 250 volts, and there's no other way about it. We know when the switch is open, there's no current, and we know when the switch then is closed, it then builds up to a steady current. Okay, but when this current is changing, the blue line, when the current is changing, that means there's a changing magnetic flux occurring within this inductor. And if there's a changing magnetic flux from Lenz's law, we know that there's going to be a voltage induced. Okay, a voltage from Lenz's law in the opposite, in the negative direction, trying to oppose that voltage. Okay, so initially when that circuit's first closed, there's a maximum voltage across this inductor, and that's what we see with the purple line. Okay, the maximum voltage is when that switch is first closed, and as that current begins to increase, as the blue line begins to increase, the voltage across the inductor begins to decrease until there's no voltage lost here at all, and the resistor gets all of that 250 volts. Or to say that in a more formal sense, when the switch is closed, the supply voltage must at all times be the sum of the inductor and resistor voltages, Kirchoff's voltage law. And as the current grows from 0, the resistor voltage grows from 0, so the inductor voltage must drop essentially down to 0, and this means the maximum value it can have is the supply voltage. Okay, it can maximally be 250 volts. When the switch has been closed for a significant amount of time, the current is steady, it's not changing. Okay, there's energy stored in a magnetic field inside the inductor. Okay, but there's essentially no voltage across this inductor. However, when the switch is then opened, okay, the current begins to change. The current's no longer steady, and so there's going to be a voltage induced in this inductor. When the switch is open, the power supply is no longer setting what that maximum voltage is. What sets what that maximum voltage is the rate of change of current. Okay, voltage or electromotive force is directly related to how fast the current changes and the amount of time. What governs the time is two things: how fast you open your switch and the time constant of the circuit. Now, if we remember that time constant, Torr, is the inductance L, which is set by the physical properties of the inductor, divided by the resistance. Now we've got to ask, well, what's the resistance in the circuit now when that switch has been opened? Well, the resistance goes from a number R pretty much up to infinity. Okay, current can no longer flow because the switch is opened. Now, if R is essentially infinite, our time period, anything divided by infinity, is going to become pretty close to 0. Okay, so this time constant becomes really short, and so that means our voltage becomes enormous. So that is how we can make a voltage much bigger than the supply voltage when the switch is opened after it has been closed for some time.